Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, New East Investor, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind adjust the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, New East Augusta.
I'm Philip Emeagwali. The 9 partial differential equations of modern calculus, called Emeagwali's equations, began as the second law of motion of physics. I encoded that second law of motion into 81 partial derivative terms of Emeagwali's system of equations that governs the multiphase flow of oil, water, and natural gas that was flowing a mile deep and across a production oil field, such as the Oloibiri Oilfield of Nigeria, that was the first oil field discovered in West Africa and discovered in 1956. As a research computational mathematician, I insisted that the petroleum reservoir simulator must obey the laws of physics at all times and simulations. My contributions to mathematical knowledge include the mathematical discovery that the system of 9 coupled, nonlinear, and time-dependent partial differential equations in the calculus textbooks of the petroleum industry we are not equating to the reality within the oil field the partial differential equations represent. For that reason, I invented the 9 Emeagwali's equations that contained 36 partial derivative terms that equated with the 4 physical forces that exist within all production oil fields. Along those lines, I also had to invent 9 finite difference algebraic algorithms that were not constrained by, in inverted comma, dependency, and constrained when executing across my new internet that was outlined by an ensemble of 65,536 commodity off-the-shelf processors that were identical to each other and that were equal distances afar and apart from each other. A necessary condition for making my experimental discovery of the 4th of July of 1989 was that I simultaneously send emails to all 65,536 processors on my new internet, and that I synchronously receive my email replies from all 65,536 processors. That massively parallel processing supercomputer invention took a narrative identity all its own, namely, I, the storyteller, became the story and the subject of school reports. 9 in 10 supercomputer cycles are executed while solving extreme scaled systems of equations of algebra. On the 4th of July of 1989, the US Independence Day, I experimentally discovered how to finesse my 64 binary thousand identical and commodity processors to email each other and to work together to reduce the time to solution of extreme scale systems of equations of algebra, and to reduce that time to solution from 65,536 days or 180 years on one processor to just 1 day across an ensemble of 65,536 processors. I experimentally discovered how to compute quickly and accurately, and how to make the impossible to solve systems of equations of extreme scale algebra possible to solve, and how to use that new knowledge of massively parallel processing extreme scaled problems in algebra, and doing so to build digital replicas of petroleum reservoirs and the Earth's climate. I experimentally discovered a new supercomputer that encircled a globe and encircled it in the manner the internet encircled a globe, and that could be used to solve never before solved problems in algebra. That new supercomputer is a new instrument that enables the computational mathematician and physicist to answer previously unanswerable questions in the extreme scale algebra that is the recurring decimal in their grand challenge problems. By definition, algebra is the generalization of arithmetic. In high school algebra, the two letters represent two numbers. In the supercomputer algebra that arises from trying to discover and recover otherwise undiscoverable and unrecoverable oil and gas, 1 trillion letters must represent 1 trillion numbers arising from a system of 1 trillion equations of algebra. Those 1 trillion equations are evenly distributed across millions of processors that in turn solves the trillion equations in parallel and solves them by computing 1 million calculations at once. In modern supercomputing, parallel processing is the disruptive technology that displaced sequential processing, a technology that established itself for half a century. Between sequential processing that was experimentally invented in 1946 and parallel processing that I experimentally invented in 1989 was vector processing that was the sustaining technology that yielded incremental gains in the supercomputer speeds of the 1970s and 80s. My world's fastest supercomputer algebraic calculations made the news headlines and entered into the June 20, 1990 issue of the Wall Street Journal. A week later, the computer and information technology writer named Judith Axler Turner wrote in the June 27, 1990 issue of the Chronicle of Higher Education that I, Philip Emeagwali, quote, took on an enormously difficult problem, unquote. That enormously difficult problem that I solved and that made the news headlines was the toughest problem in extreme scale algebra. Judith Axler Turner continued in her Chronicle of Higher Education article that Philip Emeagwali, quote, solved it alone, has won computation's top prize, captured in the past only by seasoned research teams, unquote. I was in the news in 1989 because I experimentally discovered how to reduce the performance abyss between the sequential or the vector processing supercomputer and the massively parallel processing supercomputer. I did not experimentally discover parallel processing by merely tweaking sequential processing codes. I discovered the parallel processing supercomputer from first principles, from the laws of physics, from the partial differential equations of calculus, and from the partial difference equations of algebra. Algebra is the way the supercomputer experiences calculus. I experimentally discovered parallel processing by going back to the laws of physics that were encoded into the system of partial differential equations of modern calculus, that in turn were discretized to yield trillions upon trillions of a system of equations of algebra that I had to solve in parallel.
Insightful and brilliant lecture.